Welcome to another exciting video for CG game development. My name is Nate Nestler and this is for Hyperactive Studios. So what I have before you, I've moved the plane out of the way because the plane doesn't work well for this particular example. We need more tessellation, we need more geometry, shall we say, more points to work with for a twist method here. So I've added a 3D twist, and we can do it about the X, Y, and Z axis, or Z axis. I say Z in order to make it easy to understand a Z from a C because they sound a lot alike. So, but anyhow, what I can do is I can come in here and I can start manipulating this, and you can see I can actually make it lean towards one way or the other. I'll show you how I did this mathematically. It's very cool, and you will see this in some programs like Max or some of the other 3D programs will have some of these capabilities too. But here we are. We're doing it from a vertex shader, which is going to make it super duper fast with these new methods for computation. And then, yep, we got it leaning one way, then back the other. And with this, you can make this whole thing dance if you were to key it and animate it. Or run it through some noise or something like that. But, I mean, of course, we can combine these effects. So, say I go here and then, oh, I don't know, maybe this way here. And then if I go over here, I can make it lean another way, like back this way. And so now we got it doing this whole number right here. So it's leaning that way, and the other way. So now we got it going and twisting and leaning in every axis, you know, X, Y, Z, Z. Okay, very cool. So how do we go about making this cool little effect to make it do all this weird, crazy stuff? Well, let's have a look at that now. And I'm going to set this back to 0 for each one of these in order to make life easier. And in this way, we'll get to see a little more mathematics that we saw on the sheet from the last video that was available. So, you know, in this, let's see here, language, I think it's language specification? Maybe not. Alright, not real sure which one it was in anymore. This is just a language overview here. It's probably not it. Yeah, not it. Not the release notes. Not going to be the reference. Maybe the user manual. Okay, user manual it is. Okay, yeah, so from here we'll see there was cosine and sine, but remember I talked about earlier with it's more efficient to do a sine cos function here, and then so you can compute them both at the same time. And I'll give it a nice example of why you would want to do that. Here's a sine cos one right here, and this gives you an example of how that works. And again, this is a faster, optimized way of computing. Now, I did do this for respect to some optimization here, not just shoot off the hip completely, just to show off some effect. I did actually try to take into account to make things a little more efficient than not at all. Okay, so first I created, well, this is just like the inflate one. So you can take your same inflate shader from earlier, remove the inflate part, and change it to a twist, like a twist X, twist Y, twist Z. And then you just replace the name with X here. Now it needs to go from -1 to 1, and then have a step size of 0.001 here. And its default value should be 0.0f here. And that's the same exact thing for Y and Z. Literally, it's the exact same thing. Y and Z, sorry. All you do is you can copy and paste this, and then the way to copy here is, of course, select all this with Control C, and then click over here, and Control V will let you paste just like that, right? Let's hit Control Z in order to undo, but you don't need to do that right now if you're copying and pasting. But okay, so we change that X to a Y here on this part, and then change that X to that Y. So once you get one of these set up, then you just copy and paste each one. Same thing for Z here, Z. Copy and paste that in from the X, change the X to a Z, Z, whatever you want to call it, and then a ZZ for this one right here. Okay. So with that, that sets up our twist X, Y, and Z variables here. Now, going further down here, we need to do some calculations. Now, I did do this on purpose right here. Now, I did this because I did not want to do the length function for every single one of these calculations. I only want to calculate the length of the position one time, and then simply just reference that value across each one of these for doing my angle X, Y, and Z. So, and in here it's multiplied times the twist X, Y, and Z for each one of these length pose positions. Now, the pose comes in from the actual passed into it. So these are the actual positions of the actual vertices within the from the 3D program. For instance, it would be OpenGL or DirectX passing it in to our vertex shader, just as we learned before. Once it gets passed in here, then we're finding the length of that vector. Remember that this is a vector, so coming from the origin point of the model, we find the length of that vector. Then from there, we have our angle here, so multiplied times our twist x and times our length here, and then our twist y times our length again, and twist z times our length of our vector, or the magnitude of our vector, if you want to think of it that way from a mathematics physics standpoint. Okay, so then we have float sine ln x, cos ln x, sine ln y, cos ln y. These are all floats. I'm just doing a whole series of floats, and I'm not initializing them. I'm going to initialize them here in just a second, so I don't really have to worry about it. Sine ln z and cosine ln z. So we're setting all these up to be assigned a value. So then I just pass in angle x for the x one. So then it's going to respond back to me with the sine of this x angle that's being passed in, and it's going to come back to me with the cosine of this angle for x here. So, you know, sine's going to hold this x, and then cosine this x here for this variable, like so, and like so. Okay. Same thing for the y. So we can bring in angle y that we calculated from up here, and we're just doing our sine y, and our cosine y is what is responded back from this function here. And again, for angle z, and then it gives us the value for the sine about this angle of z, and gets stored into sine ln z. So if you didn't realize that's what's going on, that's what's going on. And then this one also has cosine of this angle z, and it gets stored into this variable cos ln z right here. Okay. So then I create a position local variable that only exists for this part alone. And I set up a little smart technique here. Okay, so the way this works is when you're going to rotate about that angle, that's the angle that's the axis you're not going to manipulate. For instance, I'm not going to manipulate, say this is y here. I'm not going to manipulate the y. I'm going to keep it all the same, straight up and down. And I want to manipulate all the part going around that y. So that's going to be x and z for these points going around it. A better description here is this Euler matrix setup here. There's something else called quaternions. There's really good for rotations, but for our purposes here, we're going to look at Euler formulas. And that's how you pronounce it. It's Euler, not Euler. It's Euler. Okay, so here you can see these rotations set up about different axes. So, you know, if I want to do a rotation about z, then I need to manipulate my y and my x. You can see that here with this blue. This is making sense, hopefully. If I want to manipulate, well, that's the best way to point that out, really. Yeah. Okay. So yeah, if I want to manipulate my z, I'm going to manipulate. If I want to rotate about z, sorry, then I need to manipulate my x and my y, and that's a good example of that. So the way we do this is, if you refer back to your matrix math series here, then you'll remember the rotations matrices that was in there, where we were going over how to do the calculations for the mathematics for those matrices and how to multiply them through and such. Well, flashback from there. This is the algorithms here. So we have our cosine of angle x, cosine of angle x. Sine of angle x, negative sine of angle x, and cosine of angle x here. So I'm sorry, this should be y, because this is about y. So yeah, sorry, cosine of angle y, sine of angle y, negative sine of angle y, and cosine of angle y. Sorry, they get the used to be x, y, z, x, y, and then z. It threw me off. Should just recognize that immediately right there to tell me that's not the case. But But here you can see this is the y position here in the matrix. So therefore, that's the one, since it's getting the identity matrix multiplied through, this is the one that is not being manipulated. And we're only manipulating x and z here to rotate about y. Same thing here for x. We're not manipulating x here because we're multiplying it times 1, the identity matrix for that part of it. And then we're multiplying y and z by its values in order to manipulate these values to make them rotate about x. And the same thing for z here. We're not manipulating z. We're multiplying times the identity matrix part for that one. So it's just going to be itself. Anything times 1 is itself. So no problem there. And then since we're rotating about z, we're manipulating our x and our y. And this is the formula that you use for that. Okay, so flashback over here. That's exactly what we do for a set of our position. So I want to twist about my x. Now I did this for a very certain particular reason. Now I didn't assign a initialization value to my position. I don't need to because I'm going to do it in the very first step here. So what happens here? Well, whatever x is and our position x from our actual that's getting passed into our value from the actual vertex is going to get assigned to position x here. And then for our position y, if this has no twist value on here at all, then this is going to be 0 here, and this is going to be 0 also. So this is going to get multiplied through, and you'll have 0 here. Then when you get down to the next one, its y position is going to be assigned. And that's why it looks like the original here. And then so on and so forth, and then you end up with the z too. So if this is all set to 0, then you're going to end up having, guess what? These are going to end up being the z value here. I'm sorry, the x value here gets stored into the x. And then you're going to have zeros for your y and z. And then on the very next one, you're going to have 0 plus itself is going to give you, yes, the x, the original x. And then the y plus 0 is going to give you the y. And then the 0 plus 0 from the z here is going to give you 0. And then down here in the z one, you're going to have 0 plus x gives you x, 0 plus y gives you y, and then z plus 0 gives us z. So then you have x, y, z in here, and that's exactly what's happening, and that's why we're getting our original point set position and placement here accordingly. Now, the moment I start manipulating this, it's going to start calculating, right? Because we're going to have the length of our post. It's going to go through here. We're going to get our twist angle here for our x or whatnot. It's going to get processed through here for the amount, as I think of it as a multiplier magnifier here. So whatever we do, it's going to magnify that, right? And then that's going to determine our twist angle. And from there, let's see if I can get this back to 0. There it is. And then from there, that is going to get processed here, right? So for x, we're going to have whatever angle value it is, then times the position of y, plus the negative, angle of sine here for x times position 2. Now position 2 is going to be z, so y and z here, right? And then we have our sine x here, and our sine for the x times our y, and we're going to add that to the cosine of x times the z here position. And again, this is the angle in radians of what that is, and not a not some just random angle there. It's not a degree calculation. It's going to be the resultant of that angle that was passed in radians to get multiplied through. And that lets us manipulate and derive our position for each axis. And we do the exact same thing according to these Eulers. So again, we're going to do cosine here times our position, 1, and sine our y here, 2, times our position of 2, which again, this is x and this is z. And then we're not going to manipulate our y. And then we're going to have our negative sine y times our position 0, or x, shall we say, plus our cosine of y times our position of z. And then down here, we're going to do the same thing again, where we're going to say cosine of z times position of x plus negative sign of z times position of y. And again, because we're manipulating z, so we're not going to include z in these calculations. So you can see a mathematical pattern here for each one of these. For instance, here, this one's being manipulated about y, so can y is not in here. See this? This is x and this is z because we're not affecting y. Same thing for this one too. Y, z, no x here. Same thing for here. We have x, y, no z. So that's what's going on here too. So we have sine of z times position of x plus cosine of z times position of y. And then again, I explained the plus equals setup here. That's going to end up making it all work together as far as manipulating it. And because of the plus equals, this allows us to do a combination. That's why you have to do the plus equals. Now, we hadn't talked about the plus equals before, so let me explain mathematically how that works, because that's a new one in addition to the sine and cosines. That's another new thing that we've thrown into the mix. So the way this plus equals works is this. Okay, so this would be the same thing. Now this might throw people a little nuts here when they first see this. If you've never seen this before, this is kind of a bit trippy, but it works fine. Mathematically speaking, you can actually do this. This is allowed. You can make something equal to itself plus something else. No kidding, you can actually get away with this in programming. That's valid. That is the exact same thing as the statement right above it here. It's precisely the same thing. By doing the plus equals here, it keeps us from having to say position 2 here is equal to position 2 plus pose 2. It's just a method of letting you type it quicker and easier. So if you're doing a whole lot of coding, you've been doing this for a long time, then you know this plus equals, I mean, this whole algorithm here is quite a common one, so that you don't have to remember this all the time. And so this makes it a lot faster and easier to do this. So that makes it a lot simpler. Let's put it that way. This is just a much easier way of doing things. There's another method too to make things faster too for this kind of stuff. And instead of doing like position 2 here plus equals 1 semicolon, you can say position, assuming I can type, 2 plus plus semicolon, just like you can in C++. And so if you're familiar with that, yeah, just like in C++. Okay, so that'd be the same thing equivalent to doing this right here. That is allowed. So this saves you a lot of time. So what does this do? Okay, working from a programming for the actual computer standpoint of how things work in memory in the computer, and you're probably going, well, it's impossible. If it's plus itself and equal to itself, wouldn't it be the same thing as its original way? That makes sense. No, it works because the order of operations of a computer for how it actually computes things is what makes this work. Otherwise, yeah, you're probably right. It would be impossible. What always does this first? It's going to do things on the right hand side of the equal sign before it does anything on the left hand side. It always gets computed in that way, and you have to remember that. So now if I take my this part of the algorithm here, the computer is going to go out into memory and it's going to grab this value. Okay, so say we have in the computer's memory, let's say that position 2 here, it's holding, I don't know, a 4.532. Let's just keep it simple. Let's say a 4.0. That's simpler. Alright, so say that's floating around in memory over here, right? And so when the computer goes out and checks position 2, because it does this first before it checks this one here, right? It gets the 4.0 value. Okay, cool. And then it checks its pose value here. And let's just say it's like, I don't know, 2.0, right? And it goes and grabs that from memory. Okay, so now it has a 4 and it has a 2 in memory, and these are in two different places in memory, of course. And then it sees that it's supposed to add these two places together in memory. Okay, so it's going to do that. So it's going to be 4 plus 2 is 6, right? And then it's being told right here to assign, or shall we say store in memory in this location. So it's going to replace this 4 now with that 6. Okay, so the resultant of adding these two together is going to get reassigned back into this position here in memory of the original position of position 2, or Z, I would say, in memory. So that lets you replace that in memory. If you like, I could draw this out, maybe to make it a little clearer. That's a way of writing that out in text here real quick, but maybe that's not the clearest thing in the world, so let's just quickly kick out a new image here for doing this. Okay, so say we have this position 2 in memory. So let me just real quick alright. Alright, so say this is a stick of memory, right? And we've got it divided in half for both of these variables. Okay, so there we go. Alright, cool. Now, in the original one here, let me switch over to create a layer real quick. Okay, cool. In the original one here, like I was saying, the position 2 or Z was storing a 4.0 in there. Alright, cool. It had a 4 in it. And then in the other one here for position 2 was storing a what? A 2, right? And yes, that's really ugly, but I don't care. Alright. This has to be done, right? So then we add these two values together here, and we end up with the value of 6, which is going to get stored. That is too ugly to even allow that to go on. Alright, that's ugly too, but it's better. It's going to get stored back here in the same memory position as this one here. But we're already done with our calculation, so it no longer matters, right? So this is going to get wiped out. And we're going to get a new value put in here of 6. And that's how it looks in memory after it's done for this. So when next statement here, when we reference this part here, right, for our position, we have our plus equals 1. It's going to grab what for it? It's doing the same thing as this, so it's going to go out to memory, find a 6 here, and then it's going to add a 1 to that, right? So let's create another layer real quick here, and previous layer is now gone, and it's going to put a what? A 7, because 6 plus 1 is 7, and that's going to get stored back here in memory again. Yeah, and this still remains here. This doesn't matter anymore. I really should put that on a separate layer. Oh well. And then we get down to here, again, it's the same thing as this one above, right? So it's going to read in a what? A 7, and then it's going to add a 1 to that in memory. So the way that's going to work here, it's just like before. You can probably see the pattern at this point. If you don't, that's cool. You're about to get... Yee. Okay, let's go up to this one. About to get it here. Okay, so now we get this 8 right here, up here in memory, where that plus plus happened. So again, we're just manipulating this place in memory for that variable, and that's what's going on. And then that's why that works. And so that's how plus equal works. We can do more than just plus equal for our mathematical operations here. Be aware you can also have, I am so lazy, I'm not going to type all this out again. You could have, just like our plus, this should make it hit home quite easily. Alright, so I could just as easily do minus here, right, and do a minus equals and a minus minus. I can also come in here and do a multiply equal, and I cannot do a multiply multiply. You can only do that for plus plus and minus minus. And then I can also do it for divide to make life easier too, but I cannot do a divide divide. I can only do a divide here like this, or divide equal like that. Alright, so there's your plus, minus, multiply, and divide. And this allows us to use a shortcut method in order to make things easier. And this is particularly useful for loops when we get into doing loops and if conditional operation for logic operations. Okay, so that's basically how that works. And from a mathematical standpoint, to make all this stuff work out. And you just do it same thing in memory if you're doing the minus 1, just like it sounds. Like, for instance, if we got down here to let's say we just had, okay, let's just say this was the very next statement after the last plus plus operator, right? So we have position 2 here, minus minus. So instead of that being 8, that would have 1 deducted from 8, and you get what is it, guys? That's right, 7. Yeah, so that makes sense. So that's all there is to that. But basically that covers how that works, more or less. And of course, multiplying would, multiply the numbers in here. So 2 times 7 would be what? 14. 14 would get stored here, so on and so forth. You get the idea. And that's how that all works for all those different parts. But that's just a nice brief overview of the mathematics behind all that, and hopefully that should give you some idea of how that worked, and you would now know how to do your own, your own twist modifier, basically, as it's sometimes called in 3D applications, in order to distort and manipulate a model. And this means, just because basically because I'm doing this means I can do this in real time in a game. I could use it to do some kind of cartoony effect. This could be applied to a character's head if you want to do like some kind of outrageous cartoony animation for the character animator or something like that. For in-game capabilities, you have the ability to do this. You can use this to squash, stretch, twist, do weird stuff, with the face that you wouldn't normally be able to do with it, And this allows for really nice cartoony type actions and stuff. And you can make a teapot hop around in weird distorting ways with this twist method and such. Or, you name it, brings Beauty and the Beast to mind in particular with the teapot. But, it can be done with anything. Really, as long as there's enough geometry to work with in order to make the distortion look properly, make it look good. If there's not enough points to work with and you got to distort it, then you're just going to get a bunch of garbage. It's just not going to look good. But on a model like this where you have a lot of points to work with, it's not a ton of points. It's really not that much, especially compared to new games out there and stuff now. This is nothing. This is no big deal. This is a very few points to work with in comparison. But this is the mathematics behind this. This is how it works. If you think about a cosine and a sine, just real quick explanation of how this is working from a mathematical standpoint. You're like going, well, he didn't explain why the math works the way it works. Well, hold on. I'll make that happen. Just 1 second. Wait. If you remember 0 to 1 for sine and cosine, depending on which one you're using, oh boy, that is truly ugly. All right. Then you're going to end up with a circle if you combine sine and cosine together, with alternating periods. You know how you get the curve here? You go down like this, and then back up, and so on and so forth. So if you do that, if you combine a sine with a cosine, check it out, you get a circle. That's how it works. So if you had repeating periods here, then you would just have circle after circle after circle occurring. That's how we're able to make it rotate, because we're getting, sine you're getting one, and then cosine you're getting the other part of the angle here. So this lets you get your rotations completely to rotate about some axis, and that's how that works. Feel free to map these mathematically with a graphing calculator, or there's I'll have to hunt down. There's another program out there. I'll start pulling in the. Hopefully, in the next video, I'll pull up the. There's a program that's free out there that you can run inside of a web browser that lets you graph the different mathematical functions to help you see the order of how that math works graphically on there, and then you can use that as basically as a visual tool in order to help you understand how you need to use your math in order to manipulate your graphics. But just like I was saying earlier about the Euler here, about it creating these rotations and stuff here for x and y, that rotation is being generated because of our sine and our cosine together making that circle. I'll just do a really ugly drawing really fast here. My apologies to anyone for watching me draw insanely ugly graphics, but this will work for our purposes. Okay, so let's see how that. Well, it would help if I drew on something that was visible. That's interesting. How do I go from going to draw on something to nothing? Interesting. Okay, it's doing something weird now. Alright, let me just create a new one real quick. Oh, I need to flip that back around, sorry. Okay. There we go. Weird. Okay, so say we're getting our graph like that, and this is with our sine and our cosine combined, and it would look so much prettier than that, but this would be perfect circles. This would be a perfect circle. That would be a perfect circle, and then that would be a perfect circle, if I could only draw perfect circles, which I can't. But that's what would happen here if you were sitting there running our sine and our cosine values like so, because they're opposite of each other. They're perfectly opposite on these wavelengths. And at 1, with no manipulation here, and since these are all both being kept constant for our numbers of our angle, right? Because your x here and your y here or your z here are, we're using our x here for our sine and our x here for our cosine, so we end up getting both. And so that way they maintain exact periods and exact frequency from each other, so you don't get any kind of distortion. They're always maintain a circle that way with the mathematics here. And so this allows us to get our rotations basically based off of this for our different axes. And that's essentially how it works from a mathematical standpoint. Okay. And with that, that should cover up and explain how this particular effect works for manipulating the vertices, or points, depending on how you want to say it. Alright, thank you very much. My name is Nate Nestler, and this was CG Programming and Game Development. Thanks to Hypergraphics Studios for putting this on. Thank you very much. Bye-bye. Alright, so now on the twist here, we have one simple correction, and everything else is totally accurate except for one part here. Since we're adding to this a couple of times here, we need to divide by 3. And the reason why is because, if you do this plus this plus this, it would be 3 times the size it should be. So if we divide by 3 after adding all this together, we'll get back to the original size. It was something hard to notice while coding it, but when you drag and drop the shader onto another object, it suddenly grows 3 times the size, then it becomes noticeable. So here all you have to do is do this one edit in the code here, and the rest of the video is accurate. So just just do position divide equals 3 semicolon, and just like the plus equals, we can do a divide equals, and this will divide all the parameters for x, y, and z here for position by 3, and that fixes the problem, and then it becomes the original size, and it takes care of everything.